So thank you very much for having me. It's great to be back. I see that now New York has advanced since I was last here, and you can pay for the subway with your credit card. You cannot, of course, smile on the subway. That is still illegal. So I want to talk about the PRIA simulation suite. This is not an acronym. This is named after my wife, whose picture is in the corner there. This is a good idea. Name your suite after your wife. Here are the papers that we wrote on it, and here is the codes. Yeah, so the reason we ran this suite, this is a cosmology suite for Lyman alpha forest cosmology. So you had an introduction to Lyman alpha forest from Changhu earlier. To remind you, this is, the idea here is that this is absorption from neutral hydrogen that is in a quasar sightline. So here is a map of the dark matter density in the simulation with some gas temperature put on top. You have a sightline that goes through here, and it absorbs over densities as it goes through them here. The reason this is interesting is because this absorption traces the weakly nonlinear dark matter at redshift 2 to 5. So what I mean by that is that it's nonlinear so that we need simulations. Otherwise, it's not interesting to us because we do simulations, so we need something that needs them. But it's not nonlinear enough. It's outside of galactic halos, right? So it's weakly nonlinear in that it doesn't require too much galaxy physics. I should mention that this image and most of the images here, this image, it looks very beautiful, which tells you that I didn't make it. So it was made by my former grad student, Mingfeng, who's sitting at the back, and Ye Ying, who's sitting over there, who made this beautiful image for us. So this is a cosmological suite. This is a suite of about 50 simulations. They are 120 megaparsec boxes. They have a particle load of about 1.5 thousand cube particles. So this is about the same resolution as Illustris. The way we're able to get 50 of them is that we only run them to redshift 2, right? So the cheat here, you know, this is, of course, a wonderful suite, but the cheat is we only run to redshift 2, and everything is much easier at redshift 2. We have 50 at low resolution, and we have 3 at high resolution. We did that for a specific reason, which I'll discuss a little later. And the high-resolution simulations have 3,000 cube particles. Can I get the video? No. Not only can I not get the video, I have stopped. It's stuck there. There was a very beautiful video there that can I go back? Yeah. There should be a video that appears, but you know, it's not important. Oh, here we go. Wonderful. OK. Here we go. OK, so this is how the forest works. So the sightline goes through the gas. You see it meets an overdensity, and boom, there's a lot of absorption. It meets another density, and boom, more absorption appears. Right? So this is and right there. So this is tracing the overdensities. One thing I want you to notice is that the absorption line doesn't quite line up with the overdensity, and the reason for that is that you're looking in velocity space, so everything is redshifted a little bit by the velocity of the gas. Okay? Okay, so hopefully you should now have some sort of intuitive idea for how these sightlines come from, how these sightlines appear. These are full hydro simulations, so they have galaxy and feedback models in. The feedback model that we're using is the Astro feedback model, very slightly tweaked. Because this is a CAMELS conference, I hope that you're all sitting here thinking, aha, but wait a minute, why isn't he varying the feedback model, right? So, you know, this is a single fixed feedback model. Why doesn't his suite have some parameter which varies it? The first answer to that is that we do. We do vary one of the AGM feedback parameters. The second answer is that we stop at redshift 2. And Megan, who might be here, is Megan here? OK, Megan wrote a paper a few weeks ago explaining that the effect on the Lyman alpha statistics of the AGM feedback at redshift 2 is actually quite small, right? And there's a good reason for this. All of our feedback models are tuned to match the stellar mass function. And at redshift 2, there are not as many black holes as there are at redshift 0, right? So at redshift 2, the number of high-energy jet mode black holes is relatively small. And so the effect on the flux statistics is also relatively small. So this was done with SIMBA, which is kind of the strongest black hole feedback model that we have at the moment. So I'm reasonably confident that with Astrid, which is a bit weaker, this will not be something that's going to mess up our constraints. Okay? So I'm not saying it's insensitive, to be clear, right? All my simulations all the previous simulations do have AGM feedback in. I'm saying that it's relatively insensitive, and once you pick a model that can match the stellar mass function, you will not have the freedom to mess up the forest as well. Okay? We also have some nice gastrophysics in here. So for the laminar forest, what is relevant is hydrogen and helium ionization. We have patchy models. The model here is that we have 30 megaparsec bubbles and they kind of appear around quasars, ionize the gas, and then continue to a higher ionization region. We have parameters for these models. These affect the thermal history of the gas. And we vary them in the suite, and we marginalize them out. This is quite important because it turns out that there is a scale-dependent correlation with the ionization rate, which opens up a degeneracy with some cosmology that you're interested in. Here is a little movie of what happens. So each of these red blobs is a large helium ionization bubble. It opens up 30 megaparsecs around a quasar, denoted by the little star in the middle. And then you keep placing bubbles until you reach a desired ionization fraction. This is Phoebe's model. This is my former postdoc, Phoebe. We also have cosmological parameters. So the main goal of this is to do Lyman alpha cosmology, right? It's to measure the cosmological parameters from the Lyman alpha forest so that we can compare them to other things, such as, for example, Planck or the Dark Energy Survey. To do this, we need to parameterize the power spectrum. I have an amplitude parameter and a slope parameter. This is the same as the CMB parameterization, but the pivot scale is 0.78. That actually should be 1 over megaparsec, not h over megaparsec. Is 0.78 megaparsecs rather than 0.05 inverse megaparsecs. Notice that what we're measuring is not this. What we're measuring is the nonlinear matter power spectrum plus some kind of gas transfer function, right? So what I'm doing is I'm generating a primordial power spectrum, running it through class, running it through the simulations, and then pulling out some kind of Lyman alpha summary statistic. But these are ultimately the constraints that I'm interested in. Let me advertise. The point of this slide is that you think that I have done a lot of work and have put a lot of parameters into the simulation suite. And that is true. There are 2 parameters for the cosmology. There are 3 parameters for the helium reionization model, so the start, finish, and amplitude of heating during helium reionization. There is 1 parameter for the matter density. There is also a Hubble parameter which does absolutely nothing for the forest. The reason I put it into the suite is that when we do other things with this same suite, it will still have the Hubble rate in. There's a redshift of hydrogen reionization, and there's a heating parameter for the black hole feedback, which also does very little. And then we post-process it to add a mean Lyman alpha optical depth. So this is, broadly speaking, what we do, right? So we pick a bunch of parameters to simulate. And these are all shown by these x's here in this plot. We run a simulation for each of these parameters with MP-Gadget. We pull out a whole bunch of mock Lyman alpha spectra. We build a Gaussian process emulator for the 1D flux power spectrum, which I'll talk about in a minute. And then we take that and we plug it into a likelihood function with the existing EBOS Lyman alpha forest data, which we have not touched and which we're just using the measurement from Charbonnier 2018. And that's, this is not, I do not get any credit for this, right? So all I'm doing is the analysis, right? The credit for the data goes to the EBOS collaboration, which did a wonderful job for this. And then out of this, we'll get cosmological posterior constraints. So I said, we're going to build a Gaussian process emulator for the flux power spectrum. Let me define what this is. So I showed you this quasar spectrum, this 1D flux power, which kind of looks like that. What we do is we take the flux excess along the sight line, dividing out by the mean absorption so that we don't have to worry about continuum fitting. We Fourier transform along the sight line, and then we have a whole bunch of Fourier transform sight lines, and we average them. So this is important because if you are a cosmologist, when you think of the matter power spectrum, you have a certain intuition for how it works. And in particular, you think that all the modes are uncorrelated. This is not really the case for the 1D flux power spectrum, because when you are integrating out these two k directions, you are mixing your modes together. So many pleasant intuitions you have from other cosmological probes do not apply to the Lyman alpha forest, and this is a little bit awkward. Okay? And it also means that you're probing somewhat smaller scales than you would for the matter power spectrum. So, okay, so now this is what EBOS measures. This is the 1D flux power spectrum at redshift 2.6. I've kind of told you a little bit that you can take a matter power spectrum, run a simulation, and produce a 1D flux power spectrum. This is not what we want. What we want is to go backwards. We have a flux power spectrum, and we want to do the inverse problem to extract out the cosmological parameters and the matter power spectrum over here. So to do this, we need to build some kind of interpolating model. I'm using the Gaussian process because it's simple, and it does the job. The Gaussian process is Bayesian. I like to think of it as Bayesian function interpolation. So this will compute the probability distribution of some function f of x conditional on an input set. So here is a prior on a function, and then here it is conditioned on some data points that you've measured. The magic here is all in the kernel function, right? So the reason that you can do this and still match most functions is that you have some kind of kernel function that you pick that does what you want it to do. So this is wonderful, but it is not quite enough, right? So instead of just using a Gaussian process to interpolate between a bunch of simulations, we are using a multi-fidelity Gaussian process, which is built by Mingfeng, who is sitting at the back there. The idea here is to combine simulations at different resolutions. So you will build an emulator, a Gaussian process model, for low-resolution simulations, and then you'll use some small number of high-resolution simulations to correct it, right? So if you think about it, this is similar to what we always do. What we always do is we run one single high-resolution simulation, and then we'll argue that it gives the same answer as the low-resolution simulation, that we are converged. This is a similar thing, but now the correction is allowed to not be unity, and it is allowed to depend on cosmology. So here is a plot of the correction function between low and high resolution in our Priya simulations for our three different cosmologies, right? So you'll notice the correction does depend on cosmology just a little bit. Right, so each of these is a different simulation, and the correction function is a little bit different. The nice thing about this is that you can use your low-resolution boxes to explore the cosmological parameter space, but they don't need to be expensive simulations, right? They can all be cheap simulations, relatively low-resolution simulations, and the correction, the Gaussian process correction, will take care of the fact that they're not converged properly. Mingfeng likes to use an analogy, which I do not endorse, because I think he has the difference between low and high resolution swapped around. So the analogy here is that this is like a university, right? So there are many grad students who are low-fidelity calculators, and then there is one professor who is a high-fidelity calculator, and I correct all of their calculations to be correct. And that this is cheaper than the university just hiring 10,000 professors. So the university saves money. I'm not sure I endorse this story, because sometimes I think that he is the high fidelity and I am the low fidelity. But that's what he says. So that's schematically. So analytically, what we do, this is a Gaussian process. This F is a Gaussian process at low fidelity. And then we correct it with some multiplicative parameter, which is learned from the training set, and then some additive Gaussian process here. So it's not actually necessary to add this parameter, right? We could just have one low-fidelity Gaussian process and one correction Gaussian process. But we add this as a scale-dependent parameter because, to first order, you can see the correction is just a multiplicative term. Right? And we optimize for this rho and delta on our training set. So then we have some low-fidelity Gaussian process, some high-fidelity Gaussian process, and some correction term. And how well does it work? It works very well, thank you. So this is the, all you really care about practically is, does this interpolate accurately? This does interpolate accurately. So this is the leave one out error. We've taken our simulation suite. We've built an emulator leaving out one of the cosmological simulations. There are 3 high-resolution simulations. So this is an emulator built with about 2/3 of the data we actually have available. So this is a very conservative estimate of the emulator error because the real emulator is built with all 3. And you can see that it's about 1 to 2% accurate in practice. So I think that's pretty good. That's certainly smaller than the error bars from eBOS. And of course, we can always run more simulations if we want, and we will. So, OK, so hopefully I've now convinced you that this is a plausible thing to do, that I have done my homework, that I've run my simulations. I have a meaningful constraint on cosmology, and you're wondering what that constraint is. Here is what that constraint is. OK, so we've measured NP, which is the slope. This is equivalent to the slope to NS, the Planck slope. And we've also measured sigma 8 and the amplitude, which is written here. I have 3 chains here. This one is using all the eBOS data. This one is throwing away the 2 lowest redshift bins, this blue one. And then this red one has a prior on the helium ionization model from some other data. The first thing you'll see is that this gold chain does not agree with the red chain. This made me very concerned when I first ran the boxes, right? Because you want everything to be internally consistent, right? You don't want to have your constraints be driven by the lowest redshift bin. I sat there worrying about this for 6 to 8 months. And then the DESI collaboration released their first data set. And lo and behold, their lowest redshift bin disagrees with eBOS, right? So I think it's legitimate to throw these redshift bins away because clearly one of these is not correct, right? They disagree by more than 1 sigma, so there's something going on here. So it's legitimate to throw away this bin and only use the data that's at a redshift greater than 2.6. Notice that my argument is not based on this giving a weird answer, right? I'm not saying, oh, look, NS is odd and disagrees with Planck, so I should throw that data away. I'm saying that this data does not agree with a different measurement of the same thing. Therefore, I should throw the data away. That's a legit thing to do. OK? So let me go through the constraints. So I'm measuring the power spectrum slope as being 0.983 plus or minus 0.02. Planck gives 0.965 plus or minus 0.004. So we do agree with Planck now, right? So for the first time, the Lyman alpha forest is measuring the slope of the power spectrum in agreement with Planck, which is nice. There is strength towards, there is posterior density towards a higher power spectrum slope, which means that we are not necessarily ruling out all these nice early dark energy models that prefer the slope to be a little bit higher, which is also interesting. The other thing you might have noticed is that sigma 8 is a little bit low. So I have sigma 8 of about 0.7. Planck is, of course, 0.811. This compares with the dark energy survey weak lensing measurement of about 0.733 plus or minus 0.04. So we are lower than Planck, but in reasonable agreement with DES. The first chain I run actually came out as 0.733 plus or minus 0.02. And at that point, I was like, I am in such good agreement with the dark energy survey. This is wonderful. But of course, that was statistical. I'm maybe half a sigma off from dark energy survey, but somewhat lower than Planck. So this is a little bit interesting. This is an S8 tension at redshift 2.8. The interesting thing about this is that, as I argued, it's more difficult to make an AGM feedback explanation for this at redshift 2.8, right? It's harder to get the black holes to do things, to move the gas around enough at redshift 2.8. So if this persists in more data and becomes statistically more significant, this argues a little bit that it's actually cosmological, which I think is quite interesting. Just so that you can, it's common to put this on a plot comparing it to these things, which is the amplitude and slope of the matter power spectrum at redshift 3. And this allows you to compare my results, which are this red plot, to the Planck results here, and to previous Lyman alpha forest results. And you can see here the same thing that I said before, which is that the slope is in agreement with Planck, but the amplitude is a little bit low. Compared to the last results, they had a low slope and an amplitude that was in reasonable agreement with Planck. The shift in the mean from here to here turns out to be better simulations, basically. We have more simulations, we have better interpolation between the simulations, and that enables us to get a better answer. The larger uncertainty in the slope is because we have a helium reionization model for the first time, and this induces a scale-dependent bias on the power spectrum. And so it is, of course, degenerate with measuring the slope of the power spectrum, right? So it makes the error bars a little bit larger, which is, I guess, is annoying, right? Because you would prefer to have small error bars, but there it is. Let me finish. So what I've done, the Prior simulation suite is a large suite of cosmological simulations varying a variety of parameters. It is, for the first time, large enough that we can resolve both the Lyman alpha forest gene scale and the larger scale of the box in a single simulation. We've run a cosmological parameter constraint, and we get a slope that is in agreement with Planck and an amplitude that is low. If this is for real, which I think it is, at least as far as my analysis is concerned, then it suggests that the S8 tension persists at high redshift, which suggests that it could well be cosmological and not AGN feedback. If you just use a ballpark order of magnitude estimate using only Planck and the Lyman alpha forest data, you'll find that a neutrino mass of about 0.2 to 0.4 eV fits these results reasonably well, right? And that's because the effect of neutrinos is to suppress the power spectrum on Lyman alpha forest, but not to suppress the power spectrum on Planck scales. This is not a claim of a detection of neutrino mass, because there are other things that constrain it, and some of them place tighter constraints than 0.2 eV, right? So I am not willing to claim this at this point. In the future, we would like to look at this with the DESI data set that's coming online quite soon. I would also like to look at somewhat better statistics, such as the scattering transform, and I would like to expand it to larger scales. So thank you very much for listening.
Thank you, Simeon. Chung?
I have two questions. One is, so you right now do this student-professor enhancement thing, but you only have 3 professors. And I'm guessing those are positioned within the bounds of the lower resolution or lower fidelity mocks.
Yeah, that's right.
Are you concerned about the fact that then you have to extrapolate when you correct for the lower resolution ones outside? So like at the edges of the chain, can that affect your constraints at all?
Yeah, so these red points are the high. So what we actually do is we run the low fidelity simulations first, and then you resimulate some of the low fidelity samples at high fidelity, right? So these red points are the high fidelity simulations. We were, of course, able to cheat very slightly and run simulations in regions that are close to the maximum likelihood of the chains, right? So we're not extrapolating that much. The other thing that helps us is that the correction is actually fairly, this correction is fairly small, right? It's only between 2 and 5%, right? And the error bars are between 2 and 5% as well. So, we were almost able to just do it with single fidelity, actually. And you can see the cosmology dependence is not that large, right? So that's how we're able to get away with only 3 simulations. I'll probably run like 1 or 2 more just to be sure. But I think we're good because it's just not that big an effect, really. Yeah. Did you have a second question?
Yeah. The other was, have you thought about, right now you're treating the Lyman alpha measurement from EBOS, or I guess in the future DESI, as this pristine measurement. But you could instead also forward model the systematics.
Yes.
and incorporate that into the infrastructure you have, build the emulator on top of that.
Yes, that would be, so we do a little bit of that because we forward model the DLAs and pull them out.
I see.
That would be a good thing to do, is to forward model. So the next thing to do would be to forward model metal lines and pull them out. So yes.
Oh.
Yeah.
Chris?
Hi, great talk. You said at the start, and you used Megan Tillman's results to motivate the fact that AGN feedback has very little effect on the forest. But if I understand correctly, that was in CAMELS boxes, which are relatively small and therefore don't have the massive halos that might contribute to this. But you did show that you're varying the AGN heating rate. So could you just clarify what AGN parameters you are varying and what the conclusions are on the impact of AGN heating?
Yes, that is a very good point. This is a thermal feedback only model, right? So the AGN heating rate is the amplitude of thermal feedback. It has a very small effect. This specific parameter has a very small effect on the forest. And I can see that explicitly in the suite. It's like it's in the paper, but I think it's order of like 0.5%. It's tiny. You could argue that some stronger kinetic, like jet mode model, like Simba, would have a bigger effect. Megan finds that it doesn't. You can make an order of magnitude estimate as to how much it should be able to have an effect by counting the number of jet mode of black holes of that mass range in the simulation boxes and working out how much of a volume, if you cut out 1 megaparsec around each of them, the maximum percentage of the volume they could have on the box. And I do that in the paper, and it's also small. So I think that it's not big compared to the error bars of the survey. These are relatively large scales. If you want to write a paper telling me that I'm wrong, then you should do that.
No, thanks. Yeah, thanks.
We have time for more questions. Maybe one from Zoom.
From me. So Simeon, can you use this simulation also for dark matter, like warm dark matter and these kind of things?
There is no warm dark matter explicitly in this, and the resolution is not quite enough to do the high resolution laminar forest. But yeah, we could definitely do something very similar for warm dark matter. And that would be a great thing to do in future.
Other questions?
What is the situation, like how do you deal with when you have more than 2 fidelities? Is it just done incrementally?
It is a directed acyclic graph, and you have more learnable parameters, basically.
But in that situation, can you quantify your fidelity in the sense that if you can say that your second fidelity simulation is 4 times the mass resolution as the first one?
Oh,
so can you use that information in your multi-fidelity GP?
I think the answer is yes. Mingfeng, is the answer yes? Yes. Yeah, I think the answer is yes. It does generalize straightforwardly. Notice it says t and t-1 here, right? So that tells you there are t fidelities there. So it does generalize straightforwardly. You just have more learned parameters. We haven't used the generalization to do cosmology yet. So I haven't played with it in anger, but as far as we can see, it should work. Yeah.
Thanks. Danielle, okay. Then Ken.
Yeah, so quick question, going back to the correction, so with resolutions, so you find and allow for a cosmology dependence. So I was wondering of any plausible dependence on all the parameters,
Yes.
either feedback or even some of the reionization.
Yes. So when I say cosmology dependence, this is a dependence on any parameters in the simulation suite. Right. So in principle, it's going to be able to learn even a dependence on the AGN, a resolution dependence based on the strength of AGN feedback. Yeah. But the biggest one actually is cosmology.
You were showing how you paint the helium-2 ionization bubbles. Is that not affecting the laminar flow forest result as well?
It absolutely is affecting the laminar forest result, yes.
So then But you're still saying that AGM feedback is not important for laminar alpha forest.
Okay, yeah, that's true.
So how
Okay,
does that play out?
you're saying that's true. You're right. The helium reionization is a form of AGM feedback. Yeah. So in that sense, yes, I guess the AGM feedback is very important. Yeah.
But this should be affecting the laminar alpha forest ionization rate, right?
Yes, it is. So the way this is implemented is that the UV background is changed
to the right level, but you're saying that this anisotropy is not affecting the laminar forest statistics.
This anisotropy is definitely affecting the laminar forest statistics, yeah.
But still, you're saying it's below 1%.
I'm not saying that.
Okay.
This is affecting laminar forest statistics significantly, actually. So this helium reionization model, if you count helium reionization as a form of AGM feedback, it's having a huge effect on the forest. Because what we do is we mask, the UV background is masked in the neutral regions, and then full
have a self-shielding model.
There's a self-shielding model, yeah.
Okay.
And that it makes a big difference, actually. It's like maybe 5% or so. It heats the gas, it changes the gas temperature, and it also has a scale-dependent effect on the gas.
All right, thanks, yeah.
All right, let's thank Simeon again. All right, our next speaker is Amon.
Alrighty, thank you to the organizers for bringing us to New York right before Christmas. I think I saw more people on my walk from Penn Station than live in Princeton, so that was really refreshing. Also more Christmas trees. So, okay, but this is not my area. I'm not a simulation expert, and I'm not a machine learning expert. But I'll tell you why I started getting involved in this and why I think it's important that we really look at these with all different perspectives. So I co-lead the weak lensing team for the Dark Energy Survey, and right now it's a very exciting time. We're in the end stage of our final analysis using all 6 years of data on 150 million galaxies. And our team has made these incredible advancements to calibrate our data and to beat down our calibration uncertainties to sub-percent precision, just so that we can match the constraining power of our data. And the reality is there was almost no point, because when we come to modeling our measurements, we have these enormous uncertainties due to baryon feedback. So I teamed up with Leah Bigwood, who's a grad student working with me at Cambridge, to start digging into this. And really a more appropriate title is how extreme is too extreme? That's the question that we've been asking ourselves for the last 3 years or so. So here's our problem. The hydro simulations are increasingly more sophisticated, and they realize a wide range of complex processes and realistic galaxy properties. And the only thing we need from them in weak lensing is a prediction for the matter power spectrum and how much baryon feedback is suppressing matter compared to a dark matter only scenario. So we've seen this plot a few times today. And here I'm showing a few different state-of-the-art simulations. And you can see that there is a large uncertainty on both the amplitude and the scale extent of these predictions, spanning about 20–25%. And that's far more than we can tolerate. We need this to percent level accuracy. So shopping around as a cosmologist, this is a pretty tricky situation. In DS, we want to avoid any concerns about mismodeling the shape of this effect. And so we make the very tough choice in our standard analyses to just throw out all of our small-scale data. So on the right, I'm showing 3 panels out of 20 from our cosmic shared data vector, just to illustrate that the blue shaded regions are what we toss. So we're losing this extreme amount of information right now. And this comes at a cost. We know that this is not the best approach going forward. If we could model the full scale extent of our measurements perfectly, we would get the smaller contours, the smaller constraints on S8 that I'm showing there. So it costs us more than a factor of 2 in our power right now. So I used to spend all of my time calibrating weak lensing data until we made that plot at the end of DES year 3 that just showed we really need to do better at modeling feedback. Now, here's another way to look at the problem, or almost a worse way to look at the problem. Even if you try modeling the full extent of our data, this is how dangerous it can be. So this is where we analyze the full-scale extent of DES data, and I'm showing how the S8 value is degenerate with the strength of feedback. Here's a common approach, a newer model that came out since DES year 3, a halo model approach that's calibrated to the Bahamas simulations. And you can see that using that simulation as a prior is effectively constraining your S8 value to a specific region of that parameter space. At this point, we really tried to highlight in work I did with Georgia Staffu that if you underestimate your feedback strength, you could be biasing your S8 low. In fact, we argued that it could be that we're underestimating feedback, and that's the cause of the S8 tension altogether. So we proposed that we should stop looking at the S8 tension as the difference between low and high redshift and look at it as linear versus nonlinear scales. And then we played this game where we reanalyzed the weak lensing data, pinning it to Planck CMB cosmology. So you're saying, OK, Planck, BAO, CMB lensing, they all do a pretty good job of telling us cosmology on linear scales. And let's use the weak lensing instead to tell us about the nonlinear scales. So here we're fixing to cosmology. And that's the prediction for how much you need to suppress the matter power spectrum to resolve the S8 tension. Now, this is fantastic because that signature is what's predicted by a range of non-standard models, like dark matter models. But before we get excited, we need to rule out that that's not feedback. And as you can see, it's more extreme than the state-of-the-art simulations. So that sets up our question. How extreme is too extreme? And is that what's causing the S8 tension? Now, so with Leah, we set out to try to test the different models that had come online on the market. And I won't go into the detail of all of these in the essence of time. But mostly, our models are in some way informed by X-ray. So either, like the SPK emulator from Salcedo et al. That's built on Antilles, it has a specific X-ray prior where you're constraining your gas parameters according to a baryon fraction that comes from X-ray gas fractions, or they're calibrated to simulations which are calibrated to X-ray gas fractions. So we wanted to take a different approach. We were drawn to this highly flexible model baryonification from Roman and Oral Schneider. And we liked it because it wasn't specific to one set of, or one suite of simulations. It could reproduce a range of simulations. Now, if you model feedback for weak lensing with a truly flexible model, it's the same as throwing away your data. You just still lose the same power. So we used KSE data, the previous generation, to the beautiful measurements that Boreana showed to constrain the gas parameters. So we're looking at the stacked KSE effect from ACT and BOSS, the previous generation of measurements. At the time when we did this analysis, it was about a year ago. We hadn't had those really nice new DESI measurements yet. Now, our results are intriguing because certainly which gas observable you use to put a prior on your astrophysics changes your value of S8. So all of the X-ray constrained things were giving us a slightly lower value, about a sigma lower, than what we got if we used this very flexible model with KSE. And this is what opened our can of worms and started to raise questions about the consistency of the different views of feedback from these different gas probes. So are KSE and X-ray telling us the same story? Now we turned the question around and said, OK, we have this weak lensing and KSE data. Let's not use it for cosmology, but let's look at what the astrophysical parameter constraints are telling us about feedback. So here I'm showing the data constraints on the suppression of power due to baryon feedback. So now we can compare to the predictions that come from the hydro simulations. And you can see that with weak lensing, we get this kind of large constraint on the pink constraints that prefers a strong feedback. But including the KSE stack measurement really sharpens up that constraint, and it really prefers a very extreme feedback. And we sat on these results for about 6 months and sent it to different people who were in the area. And everyone said the same thing: way too extreme, something's wrong. This is not realistic. Now, in the end, we put it out and we argued that we're constraining feedback in a totally different way than if we were using X-ray, where we're looking at large radii far beyond the virial radius. We're looking at lower halo masses with KSE, and we're measuring higher redshifts. So really, the KSE measurements are more suited, more compatible with where we're sensitive to with weak lensing. The one criticism that we got, which we took on board, was, maybe this isn't your data. Maybe this baryonification model, sorry, Roman, is too flexible. It's giving you this unphysical response that is giving you this extreme feedback. You need to use a different model. So we teamed up with the simulators, with the Flamingo team specifically, to test this in the simulations and do a detailed analysis studying KSE in the hydrosims. We like Flamingo because they don't just have their fiducial simulation, shown by the green lines here, which are calibrated to the X-ray gas fractions, shown as the black data points, but they have these 4 other variants, where you're moving away from constraints on the gas fractions up until 8 sigma difference from the gas fractions to give you a more extreme power suppression. Now, the challenge with measuring KSE in the simulations is selecting the same galaxies that were used in your data selection. So mostly these are coming from spectroscopic samples, which have quite complicated selections. But we know that the KSE effect is scaling mostly with the halo mass. That's what's most important. So how do we get that perfectly right? The common approach is to use stellar masses, but that is dangerous for a number of reasons. One, because the stellar to halo mass relationship might not be accurate in the simulations, and 2, because we know it's not accurate in the data, but it has a large uncertainty in the data. So instead, our approach was to use galaxy-galaxy lensing measurements of the same sample and fit in the simulation to those measurements to constrain the halo mass. So galaxy-galaxy lensing is the best way to get your halo mass of a sample. You're measuring the tangential shear around stacks of the same galaxies in your KSE, and that's what gives you the excess surface mass density, the halo mass. Now, once we did that, and we measured the KSE in Flamingo, we found that we were 7 sigma. The data was 7 sigma away from the Flamingo simulation prediction. So we tried doing it in all of the other simulation variants, and we found that the best fit that we could get was from the variance that was 8 sigma away from the gas fractions. So something is weird here. The KSE is not consistent with the X-ray information. Now, we also analyzed the low Z measurements of KSE from Emmanuel Shan's paper to check that this wasn't some dependence on halo mass or redshift, as it's a slightly different sample. And we found the same thing, but to even more extreme significance. We checked with the strong AGN, the strong jet model, or variations in the stellar mass function, and none of these were changing the fact that Flamingo could not reproduce the KSE measurements. So this test confirmed Leah's results. The Flamingo F-gas minus 8 sigma prediction sits beautifully within her constraints. And we now had evidence from 2 approaches that KSE and weak lensing want more extreme feedback, from a baryonification approach and a simulation approach. Now, given this, it's still unclear what the origin of this difference is, but is it really that strange? This was highlighted earlier in Daisuke's excellent review, and I've made a less complete version of your plot, which is Nick's plot. But if you look at your KSE from low mass and C mass compared to where your X-ray constraints are coming from, and compared to where our cosmic share is peak sensitive, the mass and redshift range where it's most sensitive to, there's a large span here. So is it that we're just not, when we calibrate our hydro simulations to only the blue shaded region, which is what's most important for AGN feedback, is it that we're missing some mass dependence or some redshift dependence? The other option is the scale extent. So we typically calibrate to X-ray gas fractions, and you have no idea how far beyond the virial radius the gas is being blown. And KSE opens a new way to see that. Now, how can we tackle this moving forwards? Leah's continuing her quest of measuring KSE in all of the simulations. So here I'm showing a preliminary plot from measuring it in the Antilles suite. And we haven't matched our samples yet, so don't look at the comparison to data, which are Boreana's really nice new measurements, but rather just look at the trends. What we like about this is that Antilles is a suite of hydro simulations, 400 simulations, and they span a range of baryon fractions and therefore a range of power suppressions. And we can start to understand what KSE depends on, how it depends on mass, how it depends on redshift, and how it depends on gas fractions and baryon fractions. But really, the other way that we wanted to tackle this is to ask the question, given that there is now, we trust our evidence, there is evidence that there's extreme feedback, more extreme AGN feedback than what the simulations are predicting, is this even possible? Can we get this in our hydro simulations without breaking consistency with all of the other observations? And so Leah and I teamed up with Deborah Sajaki and the Fable hydro simulation suite to test this. So we ran about 50 different variants of the Fable simulation, sampling the parameter space around Fable. Now, this is quite a different and complementary approach to CAMELS because we're not trying to sample the space evenly to build new models. This was very hand-selected. What about this thing? Does that make it more extreme? We were just trying to see what maximizes the power suppression and doesn't break the observational consistency. So just to briefly say, the way that feedback is modeled in Fable, there are given observations, there are two modes for how feedback is operating, either the quasar mode and the radio mode. And we varied subgrid parameters in each of the modes and in both of the modes. We tried a few different things all at once. And we were testing in 40 megaparsec box to begin with, quite like the university setup, 40 megaparsecs to begin with. And then when we found models that we liked, we ran 100 megaparsec boxes. And here's what we landed on. Xfable is our best model that we got. And really, this was addressing the scale extent issue that we put out as a plausible solution to why the X-ray were giving different results to the KSC. So the way, when you're in the radio mode of feedback, the way it works in the simulation is you're ejecting energy in jets at some radius, some bubble radius, dbub. And we blew that up. And we also changed slightly which halos were going into this mode, how easily they could enter this mode. And indeed, in this simulation, and just trying 50 different boxes, it wasn't that many, and picking things out of a hat almost, or trying, what about this, what about if we did this, we could more than double the power suppression in this simulation. And we've tested it. We're just in the final stages before we put out the paper maybe next week. We've tested it against every observation that we could find in the standard hydrosimulation papers and found that it isn't breaking the consistency there. So we think this is a really promising model. And to me, it just highlights that there is flexibility. And it is, Boriana made an excellent point. There is new data coming online. And we must calibrate to that. And there are routes to do that without breaking the models that we have entirely already. So we set out to improve the feedback modeling, and this is the most critical challenge for weak lensing surveys. We didn't quite anticipate the can of worms that we would open. We thought this was a 1 PhD project, not a 4-stage PhD project. But here's the evidence so far. You can resolve the S8 tension. It is possible that the S8 tension can be resolved if you have more extreme feedback than the hydrosimulations are predicting. So far, there is a lot of evidence on the table that hasn't concretely ruled that out. Now, when we redo our analyses where we're using models for the astrophysical parameters and varying the cosmology, unlike the first quick game for a prediction to resolve the S8 tension, so when we modularize over cosmology and astrophysical parameters and loop in the KSC stacks, we get evidence for extreme data. We've ruled out the simulator's number one complaint, which is that maybe your model was too unphysical. And we've shown that in Flamingo, you cannot describe KSE measurements. And if you do, you have to disagree with your X-ray gas fractions by 8 sigma. And finally, we explored in the hydrosimulations, can we achieve this? Can we get extreme feedback without breaking the X-ray observations? And we're about to release a new simulation called Xfable. OK, thank you.
Thanks, Alex. Nick.
Thanks, Alex. That was great. For the Xfable results, have you checked against the? You know what I'm going to ask, right?
I thought you were going to ask, have you checked against the KSC, which was the one thing that we have the capability to do, and we have not done.
Just thermal SC.
We've not. We have tested some aspects of the thermal SC, but I know you asked us at Cambridge, and we should have gotten back to you.
I did. I forgot. If I did, I forgot.
You did.
Daisuke?
Yeah, great talk. My question is about how does the galaxy property look like in Xfable? Because it's been very difficult to find the feedback model that has extreme feedback and still get anything reasonable close to stellar mass halo mass relation. It's extremely fine to find that kind of model. Can you?
I don't have the most up-to-date plots, but we have tested against the stellar to halo mass relation against about 50 different observations. It's now a very long paper. It did take us a while. At one point, we'd run about 10, and we were like, this was our best guess. We're going to give up now. And we've written out clearly which things can break the model. So the obvious thing is that we need to measure KSE in it and see if it describes those, since that was the breaking point for Flamingo. But the galaxy populations look entirely realistic.
Okay, so you found the recipe that does the feedback without actually, without actually breaking the galaxy properties.
For all of the observations that we've tested against, which I've checked as many papers as I could, as this was not my area, and making sure we are reproducing them. But if there are more observations, I think this is our job, that we make a simulation, we test against some data, and we refine it and refine it. Yeah.
So, okay, I'm excited to see the galaxy plots as well. But then what about like cluster, like stack profiles, for example? So very often when you inject this much feedback, your density profiles and things like that come completely suppressed by like a lot too. I'm curious if you looked at that as well.
Yeah, I should have put more plots about the galaxy properties in here. I'm happy to chat afterwards and show you the plots that we have. Again, everything that we tested against, it is holding up. This is exactly our concern. We didn't want a model that just gave us more extreme feedback. We wanted a model that could describe every observation that we thought of.
But you did check like cluster profiles?
Yes.
Like density,
yeah.
Okay, cool.
Yeah.
Thanks.
Rihanna?
Very nice talk. I was wondering, so you said right scale differences between the X-ray and KZ is one option. The other one is mass scales, the fact that they're looking at slightly more massive objects. And I guess for KZ, we do know that if we are to isolate things at the highest mass regime, the feedback is much, much, much less. I guess I'm wondering if you've done any of these tests.
If we've checked the mass dependence of the KSE.
Right. The explanation that KSZ and X-ray are in disagreement because they're in different mass ranges.
Yes, so we've been exploring in this KSE plot, which again, ignore the comparison to the data, but rather we were looking at the trends. We have explored pulling out different mass bins, and the issue, to rule out this question, we need different gas fraction measurements or different KSE measurements. We were intrigued, I'm not sure if any of the co-authors are here, by the ERAS gas fraction measurements that came out last week. Forget the first author, but their name begins with a P, because they are very low, and they would be exactly what we need to find consistency.
And as you know, the KSU, we do have the stellar mass bins, right? The different.
In the new measurements, yes. Yeah. So we're in the process of comparing to those. But totally, I mean, I think this is a real limitation where we're at right now, is that we could do this test in Flamingo because we have 400 megaparsec boxes. And so we don't have to do any corrections to this signal. This signal that comes out of F-gas minus 8 sigma is exactly what it is. We're not multiplying the prediction by any amount. And we can see that when you look at different mass bins, you are changing the shape. So correcting for just an amplitude is a very tricky process that I'm very hesitant about. But really, we need bigger box simulations to be able to test KSE and other feedback prescriptions. That's when we try to do it in Antilles, we're hitting the same problem. Yes.
All right. Okay, one last one.
Sorry.
So here, I guess you're using the data to constrain feedback, and then you found a recipe that can do both galaxies and then reproduce the data. So just wondering, going back to the beginning of your talk, when you highlight the fact that a lot of the weak lensing data is just thrown away on scales affected by feedback. So is there hope that now we can go back there and then use the new model to sort of do cosmology down to smaller scales? And if so, then do we, I guess X-Fable might be like one solution. What do we do about, is it probably not a unique option?
Yes, so we did analyze the cosmic shade data with the KSE stacks from the older KSE measurements compared to the ones that came out in the last few months. And we do find an assay that's entirely compatible with, it almost hits bang on plug, it's almost too good. But of course, there are large error bars there, because this model is very flexible compared to what the KSE can constrain in that first measurement. There is work in progress to redo it with the new KSE measurements. I don't think it will be our path to take the X-Fable prediction and just use that as our ground truth. I don't think I would take any single simulation and use that as our ground truth. But certainly, the problem almost went from bad to worse in weak lensing, because we thought there was this range of hydrosims that we were marginalizing over, and when we dug into it, we just made the range bigger, which is exactly not what we want. So, hopefully it just got worse before it gets better, and we'll be able to hone that down.
Okay, let's thank Alex again. Okay, great. Our next speaker is Biwei. I think if I can get the AV team to set him up. Okay, we can do that.
Yeah, hello everyone. Yeah, thanks for having me. My name is Biwei, and I'm a postdoc at the Institute for Advanced Study. So today I'm going to talk about using generative models to for anomaly detection of model misspecification, basically to detect distribution shift between simulations and observations to improve the robustness of the field level weak cleansing analysis. So I'm sorry this topic is a little bit different from the one shown on the website, but hopefully the material is also interesting. Sorry, do I click? Oh, okay, yeah. Simulation-based inference is powerful. It allows us to go beyond the Gaussian likelihood. It allows us to sample the posterior really fast. So I'm going to give a really nice talk about SBI this morning, and hopefully you'll also see many other SBI talks in the following of this workshop. So, for this talk, I'm going to talk about model mean specification in SBI. So basically, SBI assumes that the training simulations, it overlaps with the reality, but when this requirement is not satisfied, which is really a concern in most SBI applications, our inference could be biased. So I really like this plot made by Paco, which shows basically this scenario. So on the right, if you train your train your SBI models on some simulations and apply it to a simulation with a different subgrid model, then your prediction could be completely wrong. So to solve the problem, we definitely need to improve our modeling and marginalize over any modeling uncertainties. But at the same time, it also needs to develop different tests to verify the reliability of the analysis. So for example, in the traditional two-point analysis, people do all these kinds of goodness of fit tests, internal consistency tests, and many other systematic null tests. So I'm going to argue that with a generative model, by generative model, I mean that we try to learn the neural, it's a neural likelihood estimator. We try to estimate the likelihood of the data. We can also do all these tests in SBI with machine learning. So let's firstly talk about the goodness of fit test, which is also known as auto-distribution detection in many machine learning literatures. So suppose we have some simulations and some test data, and they don't quite agree with each other. We train our generative model, we get a likelihood function, we run MCMC posterior analysis, we get the bias result. But this likelihood value, it actually contains additional information. So because the likelihood is essentially just the density of the training data, and if the test data is not really drawn from the training distribution, you should expect it to have a much lower density or likelihood value. So this is shown on the lower right. Basically, we expect the auto-distribution data, the data that is not drawn from the training distribution, to have a much lower likelihood compared to the training distribution. So how does this perform in practice? We have been performing these simple experiments with Kang Dell, who is a grad student from Tsinghua University. So here we train our SBI models on some weak cleansing maps from pure dark matter only simulation, so there's no baryonic effect. And then we apply it to some data with baryonic effects injected. So so here basically what I'm showing here is just the ROC curve. Because basically here we are just doing a binary classification, right? Given a data, whether we want to classify whether it's coming from the training simulation or not. So what this plot is showing is essentially just the true positive rate and false positive rate as a function of different threshold for this classification. So basically, the upper left, the curve, the better. When you have two distribution that is pretty isolated from each other, the ROC curve should be very close to the upper left. And if it's diagonal, that means the two distributions cannot be distinguished from each other. So what we show here is basically the blue and orange are summary statistics the blue is the scattering transform likelihood. The orange is the likelihood from the convolution neural network. And then the orange and the red, they are field level likelihood learned with either a diffusion model or a continuous normalizing flow model. So we see that they are all not diagonal, which means they all kind of works. But we also see that the field level actually performs much better than the summary statistics. So, which is actually pretty interesting, because if you look at the cosmological information content in the CNN compressed summary statistics, it actually agrees pretty well with the field level. So the red one is the field level here, and then the second to the right is the CNN compressed summary statistics. So in this sense, it's pretty optimal statistic, but its model misspecification performance is actually pretty bad. And before explaining this, I just want to mention that all these experiments is performed on some pretty small weak lensing maps. So we definitely expect all of them to improve as we go to realistic surveys with much larger areas. So here is just a very simplified picture to explain the previous result. So let's say this is basically our feature space of the data. And then the blue circle represent the features that depend on the cosmology. So we can use them for cosmological inference. And then the orange circle represents the features that can be impacted by the misspecified models. In this case, we are considering this baryonic feedback, but it could also correspond to other systematics. So we have this overlapping region between blue and orange, which is the reason why we get a biased cosmological inference if we don't really model the systematics really well. And then the pure blue region is not degenerate with the model misspecification, so it's pretty robust. And then the pure orange region is not degenerate with cosmological models, so we can use them for detecting model misspecification. At the field level, it tries to model everything, all the features. So it does pretty well in both cosmological inference and OOD detection. If we look at for example, the scattering transform or many other statistics, they actually try to compress the data in an unsupervised way, which means that when you design all these kernels or these coefficients, it doesn't really depend on the cosmology. So this green circle corresponds to, for example, the scattering transform. It overlaps with both the blue and orange, so it does a pretty good job in terms of cosmological inference and OOD detection. But if we look at the CNN-learned summary statistics, because the CNN compression is actually trained to maximize the information of the cosmological information in this compressed statistics, right? So it actually tries to overlap with the blue region as much as possible. And at the same time, all the other features, they are not in the loss function. So the model has no gradient or no motivation to learn all these other features, which is the reason why it doesn't perform very well for the OOD. But I also want to mention that here we assume that the CNN is trained by maximizing the cosmological information, but there are also other ways to train a compression model with some self-supervised learning or unsupervised learning, which could, in principle, do better in terms of this OOD detection task. So if we know how the model is misspecified, we could, in principle, deproject these misspecified features and learn some pretty robust features in the corresponds to the blue region. But in practice, there are different kinds of systematics, and there are also unknown unknowns, right? We can learn some features that is robust to baryonic physics, but there are other intrinsic alignments or unknown systematics, which is really hard to learn robust features to all of them. And the field level unsupervised anomaly detection method really provides a general solution to this problem. So I don't have much time, but I just want to quickly mention that we also try to use a different approach for OOD detection motivated by this multi-scale analysis. Basically, we expect that the systematics should have a different scale dependence compared to the signal. So what we do here is basically we apply some wavelet decomposition at the field level to decompose the information at different scales, and then we try to do analysis on each of them separately, and then later we can compare the information content. So this is just a demonstration on some more quick lensing maps. So you can see that when we have this kind of noise miscalibration, one of the scale is completely biased because our noise here is a white noise, so it's dominated at small scales, and the large scales is less affected. Thank you very much. So this will be our conclusion. Let me know if you have any questions.
Thanks, Biwei. So we only have time for one question, if there are any. Okay, so let's move on to the next talk. Thank you, Biwei. Our next speaker is Medlock.
Hi everyone, my name is Medlock. I'm a PhD candidate at Yale working with Daisuke Nagai. And today I'm going to be talking to you about a couple of projects I've been working on with the CAMELS simulations, looking at how fast radio bursts can provide constraints on baryonic feedback and cosmological tension. Daisuke already gave a lot of the motivation for this talk, but basically baryons, as we all know, have a complex and wide-ranging effects on the physics of our universe. And if we look at the plot on the right, which shows the ratio of the matter-power spectrum of a hydro simulation versus that of the corresponding dark matter suppression, because of baryonic effects, we see suppression at various scales, going closer from 10 down lower or smaller. And work like Matt Gebhardt's work that Daisuke touched on briefly, which looked at baryon spread, found that quantities such as that can capture the degree of suppression on the matter-power spectrum as a function of scale. But quantities like this aren't really observable. They're something you can calculate in simulations. So what we need is an observational proxy, and we propose that we can use fast radio bursts as a clean and straightforward observable for this. Just a quick reminder of what an FRB is. They're just milliseconds long, extremely energetic pulses of radio waves. And the main observable that we look at in FRBs is the dispersion measure, or DM. As a reminder, DM here stands for dispersion measure in dark matter, as it usually is referred to. And the DM tells you the electron column density along the line of sight from the host of the FRB to us. And it's also important to note that the observed dispersion measure is made up of a number of components. So I list those at the bottom of the slide, including the dispersion measure from the host, contribution from the Milky Way halo, CGM, as well as the ISM, intervening galaxies, which I refer to as DM-CGM, and then the IGM, which can be also split up into a filament contribution and a void contribution, and so on. And there are several uncertainties on all of these contributions, but for the most part, I focus on something called DM cosmic, which focuses on the IGM and intervening halo contributions. In my first paper that came out earlier this year, I used the CAMELS simulations, specifically TNG, Simba, and Astrid, to look at dispersion measure distributions at fixed redshift. And as Daisuke mentioned in his talk, depending on the subgrid model, the baryons will be spread more uniformly or less uniformly, and that directly translates to what we see in the dispersion measure distributions, where we see a wider distribution for a simulation with less uniform spread of baryons. And taking these distributions, we can think about something called the McQuart relation, or the FRB redshift dispersion measure relation, which basically tells you what DM cosmic, or DM IGM plus DM intervening halo, is as a function of redshift. And as you can see in this plot, the median relation is given by this black line, and the theoretical equation for that is listed at the top. But then at each given redshift, there's a spread and the expected DM cosmic, and we can quantify that spread with something called the F parameter. So in my first paper, I also measured the F parameter for all the simulations in the 1P sets, or the original 1P sets of TNG, Simba, and Astrid, and CAMELS. And we looked a bit of why we saw these different trends. But the main point I want to get to is that after this, we were thinking about Matt's paper and baryon spread, and we were wondering how if the F parameter could trace baryon spread, because it seems intuitive that the F parameter really depends on how far baryons are spreading away from halos. So it seems intuitive there should be a relation, and we found that there was a very strong correlation between the median baryon spread as calculated by Matt and the F parameter. And we've initially fit it with an exponential fit that we see fits the data pretty well, but we're still working on the fit. So each point in this plot is a separate simulation with its own value of F and its own value of median spread. But we were really excited about this because it looks like this relation is independent of the subgrid model. It holds over the different subgrid models and variations of feedback. So it points that FRBs, potentially the F parameter, could be a good proxy for quantities that we can measure in simulations or observable quantities that are difficult to get as a clean and straightforward measurement. So in this plot, I show the degree of suppression on the matter power spectrum, similar to Matt's plot, colored by the F parameter value, again, for the same CAMEL simulations. And we see that there is a pretty distinct correlation between the degree of suppression and the F parameter, especially for values of K below 10. And we've started also looking at potentially fitting a function of the degree of suppression as a function of K and F, but that's still in progress. And I want to also shout out really quickly that tomorrow, Chloe Neufeld is going to be talking about a poster, is going to be giving a poster about a paper that we just put out, quantifying feedback energetics in CAMELS. And I think she'll go through the details of that in her poster. But I think back to the main project, our main concern is that the current size of the CAMELS boxes, the ones that we've analyzed, the 25 megaparsec boxes, is too small to properly capture cosmic variance, which FRBs are very sensitive to. So our calculations are all biased lower, and we can't directly compare to observations at the moment. So we're working on a number of things moving forward, including redoing these calculations on the new 50 megaparsec boxes, and thinking about calibrating on other simulations like Flamingo and maybe Crocodile, and adding more subgrid models to fill out that relation of F versus baryon spread with new simulations that CAMELS has added, such as Ramses and Swift Eagle. But I think the main point I want to make is that this is all sort of a proof of concept at the moment, and that it's important to do this preparation work now, because FRB measurements are going to become exponentially more useful in the next few years. As Daisuke said, there's exponential more detections of FRBs, but the key to making constraints with FRBs is having localized FRBs, that is FRBs with host galaxies and known redshifts, and right now we only have about 100 of those. But in the next few years, with things like DSA and CHIME outriggers, we're going to have tens of thousands of well-localized FRBs, so it's key to use simulation sets like CAMELS to really prepare for that upcoming data, which will allow us to make constraints on how feedback affects the CGM and potentially the S8 tension. I'll just leave that up.
Thanks a lot, Issa. Questions?
Thanks, Issa. That was great. Like you, I'm very excited about FRBs. the McCart relation you were showing, right? I mean, that assumes that you have like a perfect subtraction of the other contributions, right?
Yes.
So how concerned are you about, say, things like the intrinsic host dispersion measure having things like very large scatter, which we think it might?
That's a project that I'm working on currently. So I know lots of observational teams are trying to constrain DM host, and Chime Outriggers is about to come out with a new paper where they've constrained DM host, and we're working on a project comparing CAMELS DM host measurements to that. So I think that's exciting. But I think in the next few years, by the time the FRBs are feasible or viable as a truly powerful constraint, I think simultaneously other teams will be working on constraining DM hosts and then DM Milky Way, which will help with that.
Thanks.
Ken?
Medlock, so I had a question about this F parameter that you were showing that it's a nice indication, but I'm still a bit confused about this meaning of this parameter because you normalize it with the cosmic DM relationship, right? So this delta is normalized by the cosmic mean, and then you're looking at the sigma. So you're kind of normalizing out the systematics of each simulation and then looking at only the scatter around it, right? But I also wonder that there's a more significant meaning to the absolute value of DM itself from each simulation, because if they have different feedback strength, obviously the cosmic DM will also be different for each simulation, right? So you're throwing out that very important information, and then you're saying, this scaling relationship is nice. But I wonder what you can, in addition, by looking at the absolute DM dependencies from different simulations, and then combine this result, you can probably get more information out of that.
Yes, I agree. It's something we're also actively looking at. I think the F parameter is a nice, simple statistic to look at, but it loses a lot of the information. So it's something we want to think about, how we can best preserve the information.
Okay, thanks.
Okay, unfortunately we're out of time. Thank you, Isa.